Looking at U-substitution with, there we go, with exponential functions. Now remember, exponential means a number to a variable power. It doesn't just mean exponents. It means you have a number to a variable power, most commonly is e to the x. If you want to print these examples I'm about to work on, they can be found at that link, bit.ly/int.temp. Anyway, moving on to example number 1. I see 2x e to the x squared, and there is my exponential piece. E to the x squared is an exponential function. E is a number to the variable power, and when you have an ugly exponent in an exponential function, you almost always, there may be exceptions, but you almost always will start by wondering what happens if you let u be that exponent. So I'm going to attempt U-substitution, seeing if this works out. And in this case, it will, because when you do your U-substitution, you need to account for du. The derivative of x squared is 2x dx, and we must identify 2x dx in the problem before I do anything else. And this one's really easy because that is already here. No changes needed. So my du is ready to go. U is right here, untouched. And so I can substitute this problem. I first take out the 2x dx and I put du in its place. I always do du before I do the u. And then I look at everything left and I have e to the u. And I hope that's an easy antiderivative. Antiderivative of e to the u is e to the u, but we do need to substitute the x squared back in. So the answer is e to the x squared plus c. So there we go. That was kind of a nice exponential function. That wasn't bad at all. Wasn't bad. You just got to get over your fear of exponentials. Let's look at this one. This is an interesting one because it's not very ugly. This is very clean. This is an exponential function. However, the exponent is not ugly. I said just a minute ago that if you have an exponential function, you typically do U-substitution by letting u be that exponent. But I said if the exponent's ugly. This exponent's not ugly, and just for the sake of making a point, I'm going to show you what happens if you let u equal x. I'm going to do this very quickly because it gets you nowhere. The derivative of x, well, is the derivative of x. So du is dx. I see it in the problem. So if you try to substitute with u equals x, you technically can do that, but it's absolutely pointless because all it does is take your function and take it from a function of x to a function of u. It does not alter the problem one bit. I have the same function that I needed to integrate or find the antiderivative of in the first place. So you never, ever, 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 ever do the substitution u equals x. It accomplishes nothing. So this problem, I'm about to do something really weird. The only thing left, the only thing in here is the entirety of 7x. So what happens if I let u equal 7 to the x? I think I said 7x just a minute ago. 7 to the x. Well, if I tried that, I need to see what the derivative of that would be. And if you remember the formula or the method or however you want to find the derivative of exponential functions, the derivative of 7 to the x is 7 to the x times the natural log of 7 dx. Right? So before I attempt any substitution, I want to first look and see, is there a du in this problem? Is 7 to the x ln 7 dx in this problem? And it almost is. I have the 7 to the x. I have the dx. All I'm missing is the natural log 7. And natural log 7 does not have any x's in it. That is a constant. And so I can squeeze a natural log 7 in here. Just like I could squeeze a 2 if needed. I could squeeze a 4 if needed. I can squeeze an ln 7. However, you have to put its reciprocal on the outside. So I'm going to put 1 over ln 7 out here. And now I actually can do substitution because I see du in the problem. Now here's the interesting thing. I see du, and that's the important part. You must see du. So when I attempt the substitution, my 1 over natural log 7 stays on the outside. On the inside, all we're left with is du. I only substitute the du because when I do that, everything's gone, just disappeared. We do not have to plug the u in. There's nowhere to plug the u. It is possible to work U-substitution problems where you use the du, but you don't use u, and that happened right here. So now we've got to look at this. What is the antiderivative of du? Well, there's a hidden 1 in there. The antiderivative of 1 du would just be u. So it's 1 over natural log 7. The antiderivative is u plus c. And then you can plug your, now I get to use the u. I didn't use it initially, but now I can plug my 7 to the x in. And the answer is 1 over natural log 7 times 7 to the x plus c. So there you go. That is how you would solve that with U-substitution. Now that said, that's a really bizarre thing to do, and it's kind of clean. It doesn't look like U-substitution. I do tell my students to add this to their memorization bank, and it turns out that if you're doing the antiderivative of an exponential function, and it's just a to the x power, it's not an ugly exponent, it's just x, not x squared, not sine x, just a to the x. The antiderivative will always be a to the x divided by the natural log of a, and I would just memorize that because it saves you from having to do this, all this bizarre U substitution that I just did. So there we go. The antiderivative of 7 to the x is 7 to the x over ln 7 plus c. Or you could do the U sub, whatever, I don't care, as long as you get the answer right. All right, so that brings me to number 31. E to the negative 3x. I think this is, nope, 2 more. Okay, so 31 is e to the negative 3x. Okay, this time I do see something slightly ugly. The exponent is negative 3x. It's not just x. So I'm going to start off by wondering what happens if I let u equal negative 3x. The derivative of that would be negative 3 dx. Can I make negative 3 dx happen? Sure. I just got to squeeze a negative 3 down here. With my dx, I'll put a negative 1/3 to offset the negative 3 that I put in the problem. And now my du is right here, ready to be used. Once I identify the du, I know it's safe to proceed with the U substitution. So the 1/3 on the outside comes along for the ride. The negative 3 dx is my du. Then I look at everything else. I have an e to the negative 3x. That will become e to the u, and the antiderivative of e to the u is e to the u. So it's going to be negative 1/3 e to the u, but I will go ahead and substitute the negative 3x. There we go. So that one ended up being really nice. Really nice. Almost as easy as the very first problem. The only thing that made this one slightly more difficult than the first problem I did is we had to insert the negative 3, unlike this first problem where the constant of 2 was already there, ready to use. All right, then the last one I want to do is 38. There's 2 things to this problem. There are a couple of ways we could go about solving this one and setting it up. I have told you that if you see an exponential function and the exponent is ugly, that you could let u equal that exponent. And it is possible to do U substitution successfully by letting u equal x squared and flushing that out. However, I'm going to make one little change because I do not like my e being in the denominator. I would rather e to the stuff be in the numerator. So before I do any substitution, I'm going to bring that e to the numerator and make my problem 5x e to the negative x squared dx. And now when I attempt substitution, I'm looking at an exponent of negative x squared, and that's going to alter my u ever so slightly. My u is now going to be negative x squared. So du would be negative 2x dx. And now we run into problem number 2. I don't like that 5 because I need it to be a negative 2. There are 2 ways we could remedy this. One of them is to think, 5 times negative 2/5. If you do negative 2/5 times 5, that will give me a negative 2, right? Negative 2/5 times 5 is negative 2. So I threw a negative 2/5 in here to ultimately give me my negative 2. So since I put a negative 2/5 in here, I can put its reciprocal. I need to put its reciprocal out here, negative 5/2. And that would work. That's just a little bit too heavy for me. I don't like that method. It works. There's nothing wrong with it. It's just too much thinking. So what I'm going to do, as soon as I realize that that 5x is not helping me, I'm going to actually just take that 5 and get it out of the problem. I'm going to move it out of the way, and I'm going to change my problem once more to 5 antiderivative of x e to the negative x squared dx. And now we're going to do the substitution. Let me move this on over. Now let's substitute. You still want to identify the du before you do anything else. I have the x, I have the dx, I'm missing a -2, so I'll put a -2, I'll have to put its reciprocal out here, -1/2. Now let's substitute, and this is about to clean up kind of nicely. So I take out the -2x dx, that's going to be my du, and so I'm left with now 5 times -1/2 is -5/2. And if you remember a minute ago, the very first method I told you to get the -2 did have a -5/2 outside. So we're at the same spot, just a slightly different thought process to get there. Antiderivative, the -2x dx is my du. E to the -x squared will become e to the u. And so my antiderivative of e to the u is e to the u. So my -5/2 on the outside comes along for the ride. E to the u is our antiderivative, and my u is -x squared plus c, and we have our answer. That 2 looks stupid. 5/2. There, that's better. So there we go. There's number 38, and there are some U-substitution examples that involve exponential functions. Hopefully that will help you a little bit.